Good morning. Today I will be presenting about knowledge graph embedding. So my presentation consists of four parts. Part one is about introduction to knowledge graphs and representations. Second part is about translation-based models. The third part is about semantic matching model, and the last one is about evaluation and benchmarking. So we will go to the first section about knowledge graphs and knowledge representation. What is a knowledge graph? So a knowledge graph is a triple of E, R, and T. E is a set of entity, R is a set of relation type, and T is a set of triples or facts. So for example, a triple small h, R, and T represent a relationship between entity. H represent the head entity, R represent the relation, and T represent the tail entities. You can see two examples here, like for example, Hanoi, capital Vietnam. So here, Hanoi is the head entity, Vietnam is the tail entity, and these two entities are related by the relation capital of. And the second example is Einstein, born in Germany, and we have the same logic. Head is a person, tail is a country, and relation is born in. How do we represent knowledge? The first way is to use symbolic representation. In symbolic representation, we represent knowledge using discrete symbol, as we have seen before. So Hanoi, capital Vietnam. This is a symbolic representation. The first advantage of this approach is that it's very precise, unambiguous, and interpretable. So if I say Hanoi, capital Vietnam, I know for sure that this means Hanoi is the capital of Vietnam. There's no ambiguity in that statement. The second advantage is that it supports formal reasoning. So if Hanoi is the capital of Vietnam and Vietnam is located in Asia, I can do a reasoning that Hanoi is located in Asia. However, there are several limitations with this approach. The first one is that it has a limited expressiveness. We cannot express some statement like Rome is 95% similar to Paris, or it can be very expensive computationally, especially for large-scale reasoning. So the second approach is to use a distributed representation. Now we will encode the knowledge as patterns distributed across vector components. For example, imagine we have R4 and we can represent Hanoi by a vector in R4. Similarly, we can represent capital of as another vector in R4, and Vietnam the same. Now we will expect our model can learn the embedding such that Hanoi plus capital of will approximately equal to Vietnam. So the advantage of this approach is that it can naturally handle uncertainty and similarity. And for example, we can quantify the similarity between Rome and Paris and Rome and Hanoi, and we can do a comparison and get something like Rome is more similar to Paris than to Hanoi. The second advantage is that it's very efficient computationally, because under the hood it's just vector and matrix multiplications and operations, and it can generalize to unseen relationship. However, the limitations is that it's less interpretable. You don't have any clear meaning for each individual vector component. So here, if I see Hanoi, the first component vector, the first component has a value of 0.2, I cannot assign any meaning to that component. So there are several relation patterns we want to capture. Here's the 5 most typical patterns. The first one is symmetry. For example, sibling of. So if head is a sibling of tail, it automatically implies that tail is a sibling of head. The second pattern is anti-symmetry. For example, greater than. So if head is greater than tail, it means that tail is not greater than head, provided that head is different from tail. The third one is the inversion. For example, the parent of and child relationships. If head is a parent of tail, then tail is a child of head. The fourth one is a composition of relations. So here I have three relations: born in, relocated in, and has a nationality. So if A was born in B and B is located in C, I can imply that A has a nationality of C. And the last one is a one-to-end relation. For example, has child. So head can have multiple children. So it ensures that relation between head and tail 1, tail 2, tail 3, up to tail n should be all true. Now we will introduce a very important component for learning embedding, which is a scoring function. A scoring function denoted by f sub r, head and tail, quantifies the plausibility of a triple H, R, and T, and high score mean more plausible triples. There are two types of scoring function. The first one is distance-based. Function of this type will use distance to assess the plausibility. For example, here we see that we add head and relation and we subtract the tail. We expect that the distance should be small. However, to be consistent with the notion of higher is better, we often negate the distance to get the scoring function, like here. The second type of scoring functions is the similarity-based. Function of this type will use inner products as a measure of similarity, as in model like RESCO. So scoring function will determine the geometry of the embedding space and define which triples are more plausible. To learn the embeddings, we follow a relatively straightforward algorithm consisting of 4 steps. The step 1 is to initialize random value for embedding of entities and relations. The second step is to compute the score of observed triple and corrupted triple. I will talk more about corrupted triple later. Third step is to update the embedding to minimize the loss, and we will repeat the step until some stopping condition is met, like some loss threshold or max epochs. The typical objective function for learning embeddings is margin-based ranking loss, and assume that we have a training set S of observed example. We will generate a corrupted sample from training set. The next step is to measure the difference between the score of negative and positive. For now, forget about gamma. Here we have the score of the corrupted sample, and here we have a score of true example. So we expect that this quantity on the right will be higher than the quantity on the left, because it's higher mean more plausible. So if we take the difference, and we expect that it should be negative or at least 0, right? So when we apply the hinge loss, so the plus sign here is just a function here, it's a max of 0 or x, it's a hinge loss. So we expect that a true example should have a high score, so this one should be negative quantity, and when we apply the hinge loss, we'll get something like 0. However, we don't just want the positive example to be scored just higher than -1. We also want the positive example to be higher by at least some values, and this is the value gamma, called the margin. And the intuition here is that the model will learn the embedding such that the positive example will score by at least a margin gamma higher than negative triple. Now we move to the second section, which is about translation-based model. The first model is TransZ, and this model was proposed by Borders et al. In 2013. In this model, entities and relations are embedded in the same vector space Rd, and the scoring function is just the negation of Euclidean distance between the sum of head and relation and the tail. So assumption or expectation is that when we add head and relation, we should get approximately equal to tail. For example, in Rd, we have a vector representation of head, and we have another vector representation of tail, and we will expect that the model will learn the relation embedding here are R, such that when we start from head, we translate by R, we get to tail. And the loss function is just the same as before, but now we replaced with the specific form. So here is the process of generating negative sample. We start with an observed triple H, R, and T, and we will corrupt either the head or the tail by replacing the head or the tail by a random entity. But we replace just only one head or tail, not both. And this is the geometric interpretation of TransZ as I illustrated before. Here's the embedding space Rd, and we have a representation of head. We translate by the vector R, and we get to the representation of tail. This is the algorithm for training TransZ. We start with input training set S, entity set E, relation R, the hyperparameter margin gamma, and embedding dimension D. The step one is initialization. So we will initialize the relation in capital R with uniform distribution. Then we will normalize the embedding of relation to unit vectors to avoid the model to cheat. We also initialize random values for entity using uniform distribution. Then we perform the loop. Inside the loop, we normalize the entity to unit vector length, and we do a sample mini batch. And for each triple in the mini batch, we generate corrupted triples for this specific example by replace the head or the tail with the random entity. Then we will include the positive and negative triple into the training mini batch. Then we update the embedding using algorithm like gradient descent based on the loss function introduced earlier. So what are the strengths and limitations of TransZ? The first strength is that it's conceptually clear and very easy to implement. The second is that it's an efficient algorithm. You can see this is the complexity of the algorithm. The third one is that it can model very well anti-symmetric and composition pattern. However, one of its limitations is that it cannot model symmetric and one-to-n relation. For example, consider one-to-n relation has child. So Barack Obama has 2 children, Malia and Sasha, right? If I start from embedding of Barack, I move by translation has child, I should get to Malia. By the same manner, I should also get to Sasha. So it requires that Malia and Sasha have the same embedding. So it's problematic because 2 separate people should have 2 different embedding. Another example about symmetric relation, for example, married to Bob married to Anna implies that Anna is also married to Bob, right? But these 2 equations imply that the relation, the embedding for relation should be the vector 0, and Bob and Anna has the same representation. So it also problematic. So here's just a summary of how expressive Transy can model the 5 uh, relation pattern. It's very good at model anti-symmetry, moderately well in modeling inversion and composition, but it cannot model symmetry in one-to-one. The next extension to Transy is Trans8, proposed by Wang et al. In 2014. In this model, entity and relation are still embedded in the same vector space Rd, but now relation is modeled by a hyperplane, not by a vector. A hyperplane has 2 components. The first one is the normal vectors, which is orthogonal to the plane, and the second one is translation vector dr, which lies on the plane. So the main idea is that we do 2 steps. The first step is to project the entities onto the relation-specific hyperplane. Then we do the translation. So this allows for different entity to have a different representation depending on which relation they are in. Mathematically, we have a triple HRT. We do the first step by computing the projection of head on the relation plane by taking the original embedding and subtract the orthogonal component with the plane. And we do the same with the tail to get the projection for the tail. And the second step is that we apply the translation on the hyperplane by imposing this condition, the same as the Transy. And the scoring function is just a Euclidean distance. And here is a geometric interpretation of Trans8. This is the embedding space Rd. We have head embedding, but now we project the head to the relation plane. Here's the plane for relation R, and we get the projection of head. We do the same for the tail, and we do the translation. So now with Trans8, we can model one-to-one relation, which is impossible with Transy. For example, we consider again the example of relation Hess-Chai. Assume we have a embedding for Obama in Rd here, and we have another embedding for Malia, another embedding for Sasha, right? And this is the plane for relation R, Hess-Chai. We first do the projection of Obama to the plane to get Obama orthogonal here, and we do the same with Malia, and we have a Malia projection. We do the same for Sasha, and we have a Sasha projection. And it's possible that on this plane, Malia and Sasha have the same representation specifically to the Hess-Chai relation. And when we do the translation, we get from projection of Obama to the 2 representation of Malia and Sasha. So it's fixed the problem of modeling one-to-one relation with Transy. So as we can see, the first strength of Trans8 is that it can model symmetric and one-to-one relation, which is not possible in Transy. The second advantage is that it's still efficient because we only introduce a little constant 2 into complexity. However, Trans8 still has some limitation. The first one is about expressiveness, because the entity and relation still share the same semantic space, Rd. And inversion and composition are now more problematic than in Transy, because there's no explicit mechanism to enforce that we can jump from one hyperplane to another hyperplane. The third extension is Transr, proposed by Lin et al. In 2015. And in this approach, entities and relations live in different vector space. So entity Hess and tail live in Rd or entity space, and relations R live in Rk or relation space, and D and K can be different. And we also have a projection matrix that map the entity onto the relation space. So here we still follow the two-step approach. The first step is to project the embedding of entity onto the relation space. For example, here we get the projection of head entity by multiply the projection matrix with the head embedding, and we do the same for the tail. And then we do the translation, same as in TransE. And the scoring function still the regular Euclidean distance, negation of Euclidean distance. And this is the geometric interpretation of trans-R. And we start with the entity space here, and this is the embedding of head. This is the original embedding of tail. We do the projection, we get the projection of head and projection of tail in the relation space, and we do the translation to get from head to tail. And with this approach, now we can model different types of relation very effectively. For example, consider a person with two relation, professional and family. So for the same person, trans-R can project the person differently into different space. So for example, when we apply the matrix works at to a person, it will extract the professional features. But if we apply the matrix has child to the same person, it will extract the family feature, which can be very different from the professional features. Again, about the strength and limitation of trans-R, the first strength is that it is the most expressive model out of three we consider so far, and it's excellent in modeling symmetric and one-to-end relations. However, it has several limitations. The first one is it's expensive computationally. So here you see this is the additional term introduced to the complexity. It also has a risk of overfitting, especially for the relations with very few training examples. And different relation space can cause a composition breakdown, like the same in the transit. And this is the summary of modeling capacity for trans-R. There are several extensions to a translation-based model class. For example, TransD and RotateE. In TransD, it addressed the complexity problem of trans-R by using dynamic projection. And in RotateE, it modeled the relations as a rotation in complex space. Now we move to the section 3 about the semantic matching model. The first model in this class is RESCO, and it is based on tensor decomposition model. So the idea is that first we model the entire knowledge graph as a 3D tensor. We can imagine the whole knowledge graph is a cube with the rows and column represent the adjacency matrix of entities. So this is E1 up to En for the rows and E1 up to En for the columns. And each slide here is a relation. So slide 1 is a relation 1, and slide 2 is a relation 2, and up to relation K, for example. And each value of the smaller cube or the cell will be 1 or 0. 1 means that the two entity have the relationship regarding to R1. For example, if here the value is 1, it means that entity E2 and E1 is related by the relation R1. If you move to the slide R2, you get the same value for relation R2. So I just repeat it here, like xikj is equal to 1 if this triple exists and 0 otherwise. And each slice Rk is just the adjacency matrix for the relation Rk. So the goal is to learn the embedding for the entity EI in RD. And if we collect all the embedding, we will get a matrix E here, which each row is a vector that is the embedding for the corresponding entity. So this is the E1 embedding. This is the EN embedding. So the way RESCO learn the embedding is that it will approximate each relation with the low rank factorization here. So this is a scoring function, and basically it means that if I multiply head by the matrix and then dot product with the tail, I should get high values because they should be similar. And the optimization process is to minimize the distance between the original vector and the low rank representation. So the strength of Fresco is that it can model very well most type of pattern due to full matrix representation, given that we have enough data. However, it has several limitations. The first one is expensive because you see here is a quadratic in terms of embedding dimension. The second one is that it has a risk of overfitting, especially for the relation with few examples. And it still has no mechanism to enforce a composition pattern like jumping from one space to another. The next model is Dismal, and it's basically just a special case of RESCO. Entity and relations are embedded in the same vector space RD, but relations are now represented by diagonal matrix, not as full matrix. And the scoring function now reduced to this one. And the main idea is that it reduced RESCO by restricting to diagonal interaction only. So because of restricting to diagonal matrices only, if you work out the scoring function, you will get the scoring of head tail is the same for the tail head, meaning that this model can model only a symmetric relation. About strength and limitations of Dismal, Dismal can perfectly model symmetric relation due to its mathematical formulation. It's efficient because this is a complexity and it's the same as TransZ. However, the limitation, as we already discussed, it can only model symmetric relation and it cannot model other relation. This slide summarizes the model capacity of the 5 models we have been discussing so far. And the key takeaways is that we don't have a perfect model. Some models are good at capturing specific type of relation, but are very bad at other type of relation. And the second takeaway is that some patterns are mathematically impossible for certain class of model. For example, Dismal, we cannot model anything other than symmetry. Or TransZ, we cannot model symmetry in one-to-one. The third takeaway is that when we add complexity like transit and transr to help one-to-one relation, it can hurt composition because we cannot have a mechanism to jump from plane to plane or space to space. And the last one is that translation model generally are good at anti-symmetry, while semantic matching model are generally good at symmetry. Now we move to last section about evaluation and benchmarking. So to evaluate the effectiveness of a embedding model, we often use a link prediction evaluation. So the link prediction task is defined as follow. For each test triple HRT, we evaluate head prediction and tail prediction. So for head prediction, we keep the tail fixed and we replace the head with entity in E, and we compute the rank for the head, the true head. the same for the tail. We keep the head fixed, and we replace the tail with the entity in E, and we compute the rank for the T. The first measure is mean ranks. It's just the average of the ranking of the head and the tail. We add rank of head and rank of tail. We divide it by 2 to take the average, and we average again across all the sample in the test. So this measure has the properties that is lower is better, because we want true prediction on the top, right? And it measures the average position of the correct entity. However, it's sensitive to outliers, and it is unbounded. The second measure is mean reciprocal rank, MRR here. The formula is almost the same as the mean rank, but now we inverse the rank of heads and inverse the rank of tail. And the meaning now is higher is better. And it emphasizes about the top position. And it's less sensitive to outliers, and also it is bounded between 0 and 1. The third measure is hits at K. So it measures the fraction of correct prediction in the top K result. So here you see if the rank of heads less than or equal to K, meaning that the score for head is within top K, then I will count 1. I here mean indicator function. And we do the same for the tail, and we take the average by divided by 2, and we average again across the test example. And meaning is that the higher the values, the better, because now the correct prediction are in the top K, and the common value for K is 1, 3, or 10, and this is maybe the most intuitive and interpretable matrix. For benchmarking on real dataset, researchers often use these datasets in academic papers. For example, FB15K contains like 15,000 entities and around like 1,300 relations with many inverse relations. Another variance is FB15K 237. It has roughly the same number of entities, but all the inverse relations are removed, and we are left with just 237 relations. And you can see there are other data sets. And this concludes my presentation. Thank you.